And before we start the lecture, let's take a look at the. Okay, let me show it from here. So this week I sent the survey for determining which way we're gonna run for the final. So I will show you the result here. Okay. So about 45% students select the term project and 27%. So if you haven't done so, you can do it now. Okay. And 27% of students select either way is fine. Okay. So in your iCampus, I already posted so I guess based on the current statistics, we're gonna use term project as our final. Okay. Okay, so from this lecture, we're gonna start learning the reinforcement learning. Okay, and this is outline for today. We're gonna from the big picture, we will see how IR works. And we will study each element in the IR, and there are several approaches in the IR. And eventually, we will come to the running environment for IR in this course. So we will introduce some the coding environment, how to test, how to actually writing some IR algorithms in this environment. Okay. First of all, the big picture of IR. So as we introduced last time, the idea behind the IR is that the agent, or we can call it AI, that learn from the environment by interacting with it and then receiving rewards and feedback for performing action. So through these iterations, then the agent gradually getting better and better, and they will react or act better than before. So for example, here, this is a video game, as I showed you last time. So the player, assume this is an AI, then the player can have the multiple actions, behaviors. So you can turn left, right, or jump, or crouching. It can also have some attack or dodging, many different kind of actions. So then the goal for this agent or this AI is that we want to maximize the reward, which is coin, right? We want to get the coin, and at the same time, meanwhile, try to avoid being killed by those monsters. Oops. So as we can see here, if you press the right, move one step, then you get 1 point, the reward. And you move one more step, turn left, turn right, then you meet the monster, then you get minus points. So you can keep doing this way, and eventually when you finish the game, if your performance is good, then you have a higher reward. If your performance is bad, then the reward is low, right? Then the formal definition of IR. IR is a framework for solving control tasks, also called decision problems, by building agents that learn from the environment by interacting with it through trial and error, and receiving rewards, either positive or negative, as unique feedback. So this is a framework we have been seeing in the last lecture. So as you can see, usually we have this diagram. We have an agent, we have an environment, and the agent can make some action toward the environment. Then the environment will move to the next state. Then the state information will be sent to the agent. At the same time, because of that action, there could be some reward. Then reward will be also sent to the agent. So the agent will get the two information sources, right? One is the state, the other one is the reward. And then we use S to represent the state, A0, so A to represent action, R to represent reward. Then the subscripts are the time step. So S0 means that the initial stage, the first step. R1, S1. S1 is the next step. R1 is after the reward, after the first action, you get the reward, right? So at the beginning, there's no reward. Only when you make an action, then there's a reward. So before jumping to this detailed how it works, we need to know one concept, which is Markov property. Okay, sometimes when we can call an IL process a Markov decision process if it follows Markov property. The Markov property is that it talks about the current state of an agent only relies on the agent only need to, based on the current state, to decide what action to take, not based on all the history data. Okay, so let me switch to later. Okay, so okay, so from the probability point of view, then we can have this. If we consider this next state is a probability distribution, then the next state will be based on the all history data, right? So this is xt, the current laser. Okay, xt is the current state. Then xt minus 1 is the last step. Then you can trace back step by step, right? And then the Markov property is that we just need to, based on the current state xt, to decide what is the next step. Okay. Then we just decide when the action or the information we need. So now back to this state. So usually in IR framework, the state we use okay. The state we use either observation state or observation space or state space. So there are two names for this space definition. Okay, so observation or state are the information our agent gets from the environment. So in case of the video game, we just saw it. So it can be a frame. So the frame in a screenshot. It can also be for example, you design an agent that do the trading, stock market trading. Then it can be the value of the certain stock, right? The state we use S to represent the state. The state S is a complete description of the state of the world. So there's no hidden information. Then because we call it a state, means it's fully observable. Observation, we use O to represent. Then it's a partial description of the state. It means that the world, the environment, we cannot fully comprehend. We cannot fully get the information. Then we can only observe this environment based on some means. Okay, then the information we got, we call it observation. We use O to represent. Through this course, we don't differentiate the observation or state. When we only differentiate when we meet some specific environment, because some environment is fully observable, some environment is not fully observable, okay? Then we will only use, most of the time we just use S to represent the environment state. So as an example, a state, a fully observed environment, we can see this chess game. Once this chess game is showing in front of you, you know all the information of this environment, right? How many these grids you have, how many soldiers, the queen, the king, all those horses, the castle, all are here. Then you know that each soldier has some behavior action, the scope. Then you know all the information here. Then you don't need to, we say this is a state space, a fully observed environment. There can also, as another example, observation. For example, this Super Mario game. At a particular time step, we can only observe a particular environment. Once we move to the next step, then there's some environment changed, and there could be new information coming to you. Then we need to make, based on the new information, to make the decision, right? So this is kind of an example for the observation. Action space. So now we are seeing these observation state spaces. Now we move to the action spaces. So come back to this original. We talk about the state spaces. Now we move to the action spaces. So what is all the actions we can do? So we define the action space is the set of all possible actions in the environment. So it's a set, okay? It can be so as we show here, it can be a discrete or continuous spaces. You know, discrete spaces, most of the time we can see here. So now we are talking about action spaces, right? Action, for example, this game, we can consider it as a discrete spaces because these agent, this AI, or this Mario can only do 4 possible actions: left, right, jump, or crouching, right? So there's no other action, no other actions it can do. So it's like a predefined game, right? And so this is the discrete spaces. So also those kind of, if you do left, you just move left, then one step. Then each step you can only do once, right? Right, and the jump and the crunching. As another example, continuous space. As an example, this is an autonomous driving vehicle. If you consider a vehicle, when you drive, you can do the acceleration from 0 to 120 kilometers per hour. So this process is continuous, right? You cannot say one step I move 1 or 10 kilometers per hour. I mean, it can be done, but we don't consider because that in that case your time step should be very small, right? So from another point of view, the system point of view, the continuous space can also be transferred to the discrete space. But generally, we consider this kind of space as a continuous space. Acceleration, if you accelerate, then the speed will be increasing. And the turning left and right. So if you're rotating the wheel, then you can turn left or turn right. So those degrees can also be the continuous. So you can turn right, turn left 30 degrees, and move a little bit back right, and turn left more, like 4.5 degrees. So it's kind of, you can continuously rotating the wheels to control these actions. So this is a definition of action space. So move to next, then come back to the original. We have been seeing this state action. Now we are looking at this reward, okay? Reward and the discounting. In this IR, when we consider reward is a cumulative reward at each time step t. So we use R tau to represent a reward at a particular step. So this tau, we use a tau, then is a trajectory sequence of state and actions. So it can be a state, it can be action together. Then it's accumulated from the time step you have t plus 1, 2, 3, 4, until all the step you have covered, okay? Then we can, shorten the writing, just use this summation, to be concise. Since now we are considering this reward, if you look at this the equations here, if you travel, like move, consider a grid word. If you move one step, another step, then you are accumulating different kind of rewards, right? So each reward has an equal weight. So you just basically does some summation of them together. Actually, there's no let's say weighted or focus. Now that's why we have this short-term or long-term reward. Consider this is a small game. So the goal of the mouse is try to maximize the benefit or the amount of cheese, right? So from here, there is one cheese. This is 3 cheeses. Then while this mouse try to get the cheese, and it need to also avoid to be caught by the cat, right? Then the thing is, if this mouse only eat the cheeses from around it, and or it can move too far away from the home to the better, the huge amount of the cheese, right? But it has some cost. It has the higher chance to be caught by the mouse. So then we call it short or long-term reward. Sometimes we need to consider, depends on the situation or environment, we need to consider what kind of purpose or like, the goal you want to achieve. You want to have a long-term reward or you want to have a short-term reward. So for this case, we introduce the discounted reward. So similar to the previous reward definition, we use R here, same, but the difference is that we add a gamma. Gamma, we call it the discount rate, okay? After the first, from the current state to the next step, okay? The gamma, and with the power based on the step, the time step number, okay? Means that if you look at here, the gamma and gamma with 2 power 2, gamma 2 power 3 cube squared, then when the long term, when this step trajectory growing, then the long term, the reward is reduced, right? It's very small because we use the gamma to discount its value. So a discount rate gamma between 0 and 1. So in practice, I mean, in real world or in the real system, most of the time we just define between the gamma between 0.95 to 0.99, okay? Then for this gamma, so the larger the gamma is, the smaller the discount, right? So if consider if not this gamma just equals 1, it just equals the previous one. There's no discount reward, right? So it means that if you go back to here, if you check this mouse, so there's no, every time it moves, then you get 1 reward, then move to another, so this is 0, 0, 0, until here, it reached the a big reward, right? And all these paths it accumulated, they consider the same. So if you look at here, if you move just 1, 2, 3, 4, 5 steps, then you get like let's say, actually there are multiple ways to reach the maximum cheese. You can move to here to get all the cheeses. You can also get from here, right? So it depends on the number of the cheeses it can get. Now, if you just consider there's no discount, you will consider the long-term goal, the long-term reward. You will see, oh, there's a bigger reward in the future. I want to get that reward. But if you add the discount, on the other hand, the smaller the gamma, if the gamma become very small, so all the rewards in the future become smaller and smaller, smaller and smaller. So we will mostly focus on the short-term reward, focus on the next step, right? So each reward will be discounted by the gamma to the exponent of the time step. And yeah, so based on this equation, we can rewrite it, shorten it to this form, right? So the k equals 0 until infinite. Then the k is the time step. We use the time step to the discount rate, and r each step worth t plus k plus 1. So because this is starting from t plus 1. So we have so far we seen all the content, the components inside of this IR framework. Okay, so how we define the state, how we define the action, how we define the reward. Now let's look at what kind of tasks like environment we can solve. Okay, a task is an instance of an IR problem. We can have 2 types of tasks. So one is episode, and the other one is continuing. Episode means that episodic means that we can have a start and ending point. Okay, it has a clear terminal state. We can stop at some point. Continuing game or task is that there's no ending point. Once you start this task or problem, try to solve the problem, there will be no termination. For example, this stock market. Once you run it, so every day you can keep running it, right? And the stock market will keep updating as long as the time goes by. And for this game, so each let's say each game you have a goal to reach that. Once you reach that goal, then you finish the game. Then this task is stopped. So we call it episodic task. So similar to the previous one, now we come to this concept of exploration and exploitation, the trade-off. Exploration is exploring the environment by trying random actions to find more information about the environment, okay? But on the other hand, exploitation is trying to exploit known information to maximize the reward. So there's 2 patterns to make the decision. For example, you have your knowledge base, you know something, then you probably sometimes you want to make the decision based on your known knowledge, right? And there's also sometimes then you feel like I want to take some risk to choose something I don't know. I want to experience new things. We call it exploration. So this kind of pattern also happens in the IR. Let's take a look at this example. Similar to the previous one, this setting, this task is that, so this mouse, surrounding this mouse, there are cheese, right? So, but this cheese is infinite, but each time step, it can only get 1. So this infinite. And so it means that if you move 1 step, you will get 1 plus 1 reward. We call it exploitation. Then there's a huge cheese located on the top left corner. And if it's a huge reward, right? Let's say plus 1,000 reward. Now this mouse need to make the decision whether it just, so actually there's some cost here, right? Risks here. Whether it just, because it can see, it's familiar with the surrounding environment, it just moving around to get the cheese. But the reward is slow, right? It's small and slow. You need to keep moving to get this reward, the cheese, right? Or you sometimes this mouse just become not satisfied. You want to, okay, so every day, for example, just one day it can only move one step, so it can only move one. So each day it can only have one cheese, but it's not. It still feels hungry. It wants to get more, right? Then there's one day it can move and move to here. So once this mouse get this reward, this cheese, so perhaps it just fulfills the whole year's storage. So it can just move the cheese to its home and enjoy the cheese. It doesn't need to walk anymore. Doesn't need to walk around. So this is kind of a EE trade-off, we call it. In the IR problems, most of the time, we're gonna have this trade-off. And then we need to define a rule that helps to handle this trade-off. So as a summary, exploration, trying to add random actions in order to find more information about the environment. So if this mouse will try to explore this environment and find the maximum benefit for it. On the other hand, exploitation, using known information to maximize the reward. It doesn't want to move far, just check the neighbor information, then just keep moving back here and there to get the reward. Okay. Now, apart from this trade-off, now we move to what kind of approaches or methods we can solve this IR problems. Basically, we have two types of methods or approaches: policy-based or value-based. So before jumping into these two methods, we first take a look at what is a policy. Okay, we use pi to represent a policy. The agent's brain. Okay, we can say it's like a strategy for the agent to make the decision. It tells us that what action to take given the state we are in. So we are in a particular state, then we want to make a decision. This policy is a kind of rule. That based on this rule, we make the decision. So this rule should there's a good policy, the bad policy. Yeah. If the bad policy, probably you will get the bad reward, the lower reward, right? Total reward. So it defines the agent behavior at the given time. So as you can see here, you have a state, then the policy, we use the pi, based on this state. So you can consider you learned the machine learning or other background. So you can consider this is a function or Python. It's a pi is a function. So you give a input state, then this pi will generate a good action for you. So it will decide which action you need to take. So our goal is that to find the optimal policy pi star, okay? The policy that can maximize the expected return. So when we talk about the expected return, means that the cumulative reward, so when the agent acts according to it. So most of the time we find this pi star through training, and but at the beginning for some foundation problems or tasks, there's a iteration. There's a way, so we can use some equation to iterate, find the optimal policy. But for some complicated task, most of the time in the real world task is complicated. We cannot find a very concise way, algorithm to find the optimal policy. So in that case, we need to get it through the training. So then how to find the optimal pi star? Similar, there are two major approaches to train our agent to find the optimal policy, pi star, either directly or indirectly. So if you just teach the agent to how to act, how to move, how to make an action, then based on the current state, we call it policy-based method. On the other hand, it's an indirect method that we just teach the agent to learn which state is more valuable and take the action that leads to more valuable states. Okay, so when we talk about, for example, here, which state is more valuable? So you have multiple options. Then among those options, you choose the most valuable option and take the action to reach that state. So in this case, we call it value-based method. So yeah, from another point of view is that the policy-based method just give you a direct instruction how you should walk, how you should move, how you should act. Value-based is that it will give you some data, then you based on those numbers to decide which action you need to take to reach that better state. Okay, that's why we call it value-based. Value is kind of the data or matrix or different kind of information. Now, let's first take a look at this policy-based methods. Okay. So far, any questions? Okay. So for a policy-based method, we learn this policy directly, right? For example, here, this is you have this grid word. So you have each step has this rectangle. This robot AI or agent need to search for this the goal, right? We can define different kind of policy for each step. For example, at the beginning, it moved at the entrance for this grid word. It just has one policy, the action, just move to the right. If this agent somehow move in at this state, the policy, the action from this policy is just move upward, right? Then move to the next state, it also has a policy, the action to move to the upward. So all these instructions, rules are the policy we try to design, try to search for, try to get. So formally, we can say it. Formally, you can say it. You define a mapping from each state to the best corresponding action. Okay. So this is one state, and the best action for this state is to turn right. Then this state, the best action for this state is to move downward. Alternatively, it could also define a probability distribution over the set of possible actions at the state. So, for example, here, if you are in this state, it can move up, right, or down, right? Up and down or right. So we can assign some probability to the up or down. So in this case, we can assign like 10% of probability to move to up, like 30% or 40% to this part, and we can assign like 60% of probability to this direction. So now the agent need to use this probability distribution to decide the best the action, right? I mean, there is a chance that it moved to the here, but from here, it's a very bad action, the decision, right? Then you need to move back. So but at this time, the reward will become low. You will see, okay, this is not a good decision. So yeah, as we mentioned, so formally we need to like define this kind of policy-based method. There are two types of policies: deterministic or stochastic. So stochastic is a probability distribution, right? So we make a decision based on a probability distribution. As you can see, so with this, take a look at the first one, deterministic. So a policy at a given state will always return the same action. So we use this equation formula to define this kind of a policy. A equals, so we have this is a policy pi. Then you give the input state S. Then we output an action. So this is a deterministic. So most of the time, this we call it also we design a table to map, right? Because you remember when we talk about this policy is a mapping from the state to an action. So whenever you are in a particular state, then we map to the best action you need to take. So this so you can make a table, like two columns table, the state and A. And if you are in state 1, then you make an action. State 2, another action. State 3, another action. So yeah, this is kind of deterministic policy. On the other hand, stochastic policy. So the policy definition become a probability, right? Based on the current, under the condition of the current state, for this action will follow the probability distribution. So this distribution is over the set of action given the state. So based on the current state, this A become a random variable. This is a set of action. So it has multiple options. Okay, it can be a continuous or discrete. But in our case, for the simple example, we just consider it as a discrete random variable. So for example, you have a state S0, then you give the input. So now we are considering this probability distribution, stochastic policy. Based on this state 0, then we have an action distribution. The action distribution is that you can turn left with the 0.1 probability, turn left with 0.7 probability, turn right, or 0.2 probability to jump. So among these options, this is a distribution, right? So the summation should be 1, right? Then by following this distribution, you select an action, right? Most of the time, we choose the right. Yeah, move to the right, then we will be chosen. But I mean, sometimes it just like jump or turn left. It could happen. Okay. Now this is policy-based method. Now we move to the value-based method. So value-based method relies on how valuable the data of a state. Okay, we learn a value function. So now, yeah, so we use the v pi s to represent this value function. Okay, now we rely on a value function to map a state to an expected value of being at that state. So it's a little bit kind of different from the policy base, right? So means that we need to calculate the expected value of being at that state. So formally we use this v pi s to represent the value function. So means that this value function v with this it's a design policy, right? So we use pi to represent this value-based to decide to determine the policy with this state. So starting at the state S, so we have a set of the states at particular time t equals, so S, this is the one state. Now the expected discounted return, the reward, we just put the previously the reward, the return we defined, right? The RT plus 1 gamma RT plus 2 continuously. So we have this discount rate. Then we try to find the expectation of this value. Then in this case, actually we can calculate for a particular state, we can calculate a value, okay? Also remember that actually a little bit different from the previous reward definition. When we write here, this is a capital R. So now this R become a random variable instead of the scalar or number, right? So actually previously, if you would see here, the reward is a small r, that is a capital R, right? Now it become a random variable instead of those fixed number. Okay, so then with this approach, then we can, so this is a kind of we can calculate expected value of that at that state, and we assign to this value function. So the value of the state is the expected discounted return the agent can get if it starts in that state and then acts according to our policy. As an example, you see here. So you see, according to the value function, so at each step, so our policy will select the state with the biggest value defined by the value function. So actually, if you look at here, this is a value function, but in this case, actually, we already defined the value function. The value is already calculated here. -7, -6, -5, until -1. And other states will have a different value, -7, -8. So if you consider this agent move to this location, and you get the reward -7, right? Move to, because there's no other option, they just move to the next. But this state, it has two options, either -5 or -7. So if you calculate if we choose to the -7, it cannot reach to that goal, and you need to move back. Then there's their reward, the accumulated reward will be much worse, right? They will move to -7, -8, move back again, -7, -6, and move to -5, -4. Then you can also just directly choose -5, -4. So there's no other option, okay? Just choose the shortest path it can get. So in this case, the -7, -6, -5, and so on to reach the goal, right? So then this is the value-based method. So the policy is that select the state with the biggest value, okay? Then where are these value comes from? We need to calculate based on the reward, okay? The reward is from the environment. So the environment defines those rewards. Then those, for example, if you look at there's a complicated example. So for example, the SpaceX, Elon Musk, they are trying to land their spaceship in the Mars. So for landing the spaceship on the Mars, actually the Mars is the environment. It has different gravity, and they say all kinds of the winding speed and all kinds of those the solar energy stuff, all those environment information. So if you now the Starship need to choose the best action at each time step based on the environment, then they can calculate at each state it has a value. So which value will be a better choice? So you just choose the best value you can get, then make that decision, then move to the next state. Okay, so this is those values should we can get those values based on the environment. So those environment we will look at later. How would those environment decide those values later? Okay. So in summary, so two approaches to find optimal policy pi star. Left-hand policy-based method and the value-based method. The policy-based method train the agent to learn which action to take given a state. Okay, and the value-based method train the agent to learn which state is more valuable and take the action that leads to it. Okay. Now, actually, so far we just we already finished all the definition or like way, the means of approaches to solve this RL framework, RL problems. We have this agent, environment, state and reward actions. Then for the agent has a policy, it needs to make the decision to take an action. The policy can be directly defined policy. We call it policy-based method. It can also be value-based method, right? Value. Now, the value-based method is based on the reward from the environment. Okay, the environment will give some information about those values. Then based on the value function, we select the most valuable state to act, to reach to that state. Then we just continuously running this process. Then eventually the agent need to find the optimal policy for it for a particular environment or for a particular task. Okay, let's take 10 minutes break. Okay. Okay. So, okay. So, for example, here, when this example, when we get this value-based method, so the policy will select the state with the biggest value defined by the value function. So this biggest value is already calculated value based on the value function. But how to calculate this value? Actually, this value is calculated based on all the surrounding reward information. Okay, if you are at this state, you have all the surrounding reward information, then we calculate this value. But for this example, actually, we didn't define those surrounding value. So, I mean, it's just a simple example, simplified example to see that what kind of the decision we need to make at this state. For example, -6, -7, and -5. So the value function already calculated the two values. This state is -7, this state is -5. That means how we calculate this -5 actually depends on other areas value, reward value. Okay, so we will look at actually for calculating this kind of value, there's some theory we will look at in the next lecture. So we need to the so-called Bearman equation. So actually, there's an iterative way to calculate those values. Okay. Okay. So from in the next lecture, we will look at the iterative way to calculate this value function. There's an algorithm, the very concise algorithm to iteratively calculate those value. Okay. And okay, let's resume our lecture. So yeah, some students have this question about this value-based method. When we define this value function, then it calculates the expected value of being at the state. So, but this expected value depends on all other future step value, right? And also when we calculate the expected value for a particular reward, actually this random variable, it depends on the all other possible distribution. Okay. So we will look at how later how to solve this, how to calculate this value, and by some like a grid fully defined grid word. So it means that each rectangle will have a reward value. Then in that case, we can fully calculate this value for a particular state. And another question from students is that when we talk about this reward, here actually reward, when we use the rewards, okay, it's a cumulative reward at each time step. So the concept is different from this Markov property. So Markov property defines the state. Okay, so it means that we only need the current state to decide which action to take instead of all the history state. So actually, if you can consider that the current state is already accumulated result of the history. Okay, so the reason the result you are in this current state is already accumulated rewards or calculated. Now you will select in this state. That's why we can consider this Markov property. So we can, based on only the current state, then we make the next action because the current state already includes the history data. Then come back to this reward. But the reward itself, when we define the reward, it's a cumulative reward at each time step. It's not only for particular, only based on the current state reward. It's a cumulative reward because if you consider the step by step. Yeah. Okay. So we will see some example later. Okay. Now we come to this model in RL. A model in RL is an agent representation of the environment. Okay, so now actually there is a different concept here, right? If you look at here, the original diagram of RL, you have an agent, you have an environment. So far, we learned is that we define the policy or value function, policy-based method or value-based method to interact with the environment. Then the environment gives the reward, right? Now, the agent itself can also, if it has some information about the environment, it can also build a model about the environment, okay? If this, for example, we call it model-based method. So it can be a model-based or model-free. It can have or cannot. Yeah. Go back to the previous next here. Okay. So the difference is that the model predicts what the environment next will do. Okay. So it's like previously we just concerned about the action. Now this model will deal with the environment, will generate the state for us. It will predict the next state, predict the next reward. So it's like you build a map for this environment. Even though this model may be accurate, may not be accurate, but it at least gives some information about this. This map gives some information about this world, this environment. Then we, based on this model, we predict the next state and predict the next reward. Okay, so it means that actually you need to have a pre-information about this environment. That's why we can build a model. For example, here I use a recycling robot. So we just simplify. Okay, we use this diagram. For example, the battery, the agent itself has this battery, high and low, and you need to evaluate. Then it can have, based on this environment, it can doing wait. It can also doing search. While doing the search, if the battery become low, it need to come back to the recharging station, then do the recharging. In this recharging station, you can also do search and or wait. So while searching, so you can do the recharging to be high and move to another state. Okay, so it's kind of all, we call this, we build this diagram or relationship diagram to represent the environment. Based on this environment, the model, then the agent can, based on this model, the agent can get the predicted state and predict the reward. Okay, but the thing is, in some scenarios, it will be good, but in some scenarios, it's difficult to get the environment information. If you, for example, similar example, if you you want to land a spaceship in the Mars is unknown territory, unknown land for us. Actually, we don't know much about some unknown factors there may impact our landing machine, right? So in that case, it will be difficult to build this model for an agent to make the prediction for the next state and make the prediction for the reward. But for some cases, it is possible to build the model. In this case, recycling robot, there also can be for example, the parking lots inside the campus. So you have these underground parking lots. Then you can't just define their model. The environment can have different status, right? Can so how many parking lots are available? And when the new parked car occupied one slot, it will be reducing. So each step, it will generate a new state, predict the next state and the reward. So when the parking lot become crowded, maybe this reward, we can predict the reward will become lower because it's crowded. You should not park there anymore. If it's a lot of spaces, then reward may be higher. So yeah, you are available, you are free to park. And also the state, right? So this kind of environment, we may build a model for the agent. Now we just, based on so far what we learned, we can categorize the RL agents. One is value-based, the other one is policy-based. Value-based simply just no policy, purely based on the value function. Policy-based only relies on policy, no value function. Then there is a mixed method called actor critic. It has both policy and value function. Okay, so means actually you can, from the name, you can see why we have policy and value function. The actor can be the policy, then critic can be a value function, means that they can mutually influence with each other and update the action we want to make. Then if we consider whether we have a model or not, this should be model, M-O-D-E-L, model-based, model-free, and model-based. This is if it's a model-free, there will be no model. So the IR agent will only act based on policy and or value function. If it's a model-based, there is a model, and it will get the information from the model. At the same time, we also use the policy and or value function to combine them together to make a better choice, to make a better action. Okay. So yeah, based on all those background information, we have this a taxonomy of IR algorithms. But so you see here at the top is IR algorithms, and we divide into model free and the model based. So model free has a bigger group. Okay, model based is a little bit limited because the model is difficult to get. You want to build the model, it will be difficult. Then below the model free IR, there are two ways. One is policy optimization. This is policy based. Another one is actually value based, Q learning. We call it Q learning. Q is quality. Okay, we need to evaluate the quality of a value function. That's why we call it Q learning. Okay. Below them are all those different kind of algorithms, those famous algorithms. Okay, policy gradient, A to C, A3 to C, PPO. We may later in this lecture we may select some of them to study, some important one, and even for example, in the last lecture we look at this PPO. It's a proximal policy optimization approach. In the ChatGPT, they use this PPO optimization method to optimize their policy. Okay, but seems this PPO is a little bit like it requires a lot of the huge amount of data and labeled data, and that's why they need the human intervene to label the data. Yeah. So we may look at, okay, this is for model free IR. There's also model based. And under the model based, there are two ways: learn the model and given the model. So we all know that given the model is difficult, right? Actually, there's not much the approaches to do that. Then learn the model. Then the thing is that we want to have the model. Then we can use some way to learn the model, to build the model that describe the environment. So there are multiple ways here. So mostly these kind of approaches usually they are targeting some particular or very general environment. So they want to build those environment model. And it become very complicated. For example, these world models. So it's kind of build this a real world model. It has a lot of those information, ocean, land, sea, those information. Yeah. Okay. So far we covered most of the key concept of the IR and how internally how they are working, and how we can. There are different kind of approaches. Okay. Now we will also want to get some like hands-on experience how we can actually write some like IR methods or some to calculate, to guide an IR agent to work. So for that purpose, we rely on the gymnasium, a Python library running IR. Okay, so we're gonna introduce this like a library in Python. So this library was previously maintained by the OpenAI since last year. Yeah, they moved to a new foundation, so called Rama Foundation, like to maintain this. I guess so. In their webpage, they say why they want to move this from this environment to a new organization, because I guess because the maintenance of this platform, this library is kind of diverse. I guess due to pandemic, some people just cannot maintain this environment. Then they become very kind of not very actively maintained. That's why they move to a new organization. They can have a more active maintain the environment. So basically, this environment is that it provides an API standard for RL with a diverse collection of reference environments. So actually, inside of this library, it has a lot of environments, from the simple the grid world, can also have those 2D environment. You can also have those different kind of games, Atari games. Yeah, it can also include those Mujoko. It's a multi-joint some dynamic those machine. It's like those mechanical machines. Okay, the mountain car, pendulum. So we will look at it later. Okay, so it's like, so need to be remember that is for single agent reinforcement learning. Okay, when we use this gene, that in short we just call it gene. Okay, it's mostly designed for the single agent environment. If you want to deal with multi-agent, means that, so it's like there's some interaction among different agents. Then there's another environment based on the gene. So they have a higher level environment. So yeah. So as you can see here, in this library, gene library, it has provide all the different kind of environment you can test your IR algorithms. So these two joint, we call it cut pool. So this one also, that's a mountain car, and this is those cheetah, to mimic the cheetah running, how to make this kind of model to run like a cheetah fast. And this is the Kumojo. So this one, Mujoko, multi-joint machine to control, to move some the car to some destination. And the last one is a racing car. So they provide, so for this car, it can move to left or right or acceleration, right? Then they have a predefined this track. You need to follow this track to train to make this car to reach its destination. Okay, actually there's a lot of more environment we can explore. How you can use it? You can use it either in the Google Colab or run locally in your computer. In the terminal, you can install it in the Linux OS like Ubuntu. So you can install it. So if you are using the Google Colab, you can just apt install following this command. And if you want to install it in your local computer, Linux OS, then that might be some extra library need to be installed from the Python. Okay, so usage. So yeah, if you open in the iCampus, you check the slides and the link. I already shared the sample code in Google Colab. So I already write some code there, and you can check how it works. So then apart from that, then if you want to use this gene, how you can use we just import this gymnasium as gene. Then the other, this is for plotting, is a NumPy for deal with data. And this matplot library inline is to showing the figures in the Google Colab. Okay, so if you click this link, Okay, click this link. So let me. Okay. Okay. I need to switch the. So, okay, it's not showing. Yeah. So, yeah, everyone open, right? Can you open this one? Can you open? So in the slides, in the iCampus slide, there's a link. You open it. So I already shared anyone with the link. You can open it. So this is a hands-on code that to show you how you can do it. Duplicate. I mean, if it's you don't have it, it's also okay. Let me share screen. Yeah. Okay. What's going on? Share. Okay, it's sharing. Okay. So now let me. So this is Google Colab. So whenever you have a Google account, you can use the Google Colab. So when you open it, the link, you see that how you can run some install the gem inside of this Google Colab. Okay. So at the beginning, you see this code. At the beginning, if you click run, it will. So how many of you have used the Colab before? 1, 2, 3. Okay, most of you already use. Okay, that's good. So yeah, you can install this Colab, this like packet. The first one is the Swig and the CMake. So there's 2 packets for running the gem. Then after that, you can install gem and gem. So then how many of you have used this gem? Knew this gem before? 1? Okay. So yeah, so you can install, and so it takes some time. So for example, if I just run it from here, it takes like maybe 5 minutes to install, less than 5 minutes to install the Swig. Swig is slow actually. So now it's yeah, it's running, installing. So yeah, now it's building wheels for the collected package. So while waiting, so after a while we'll finish the building. Now after building those, it means that you already successfully installed those library. Now you can just import. So mostly this is the most important part, to import this gymnasium as gym. Then others are for the plotting purpose, okay? NumPy is for the data, and the 2 lines for the plotting. After that, we can run this, we just directly use the environment from this gym, Luna Lander V2. Then we load this environment and we iterated this process 1,000 times. And it will, for example, we will look at it later. So it's like this environment, okay? We build this environment, gym, make, period make. So this make is the API from this gym. It will make this environment. Then with the random mode, this random mode is for the visualization, okay? Visualization, they have multiple choices, options. Then it equals to this environment. With this environment, at the beginning, we need to reset the environment because this environment can include the previous data, okay? Reset everything. Now we run this iteration. With this iteration, so the important part is that we can, so inside of this environment, it has action space. It also has the observation space, actually means the state, right? State space. So it has action space and observation. So in this case, actually, we use this sample. This sample method is just randomly select an action from this action space. Then we assign to action. We send this action to this environment step action. So we send this action. This is the action we choose. Then we input to this step. This step is the like time step. Each time step we run one action. After that, this environment will return the state information, then the reward, whether it's terminated or truncated, and other information. Okay, all those information. And this for the showing animation. So eventually there is a terminated or truncated status. Then once that's done, then we just reset the environment, then finish. Okay. The installation is finished. Okay. It's a box 2D pi. And now we just run this simple just import. After that, you will see the running process. Okay. A little bit slow. If you run it locally, it will be fast. So because online, so you see they have the action spaces, turn left, turn right, or acceleration down. Okay, because currently we just choose the random actions. Random action, right? So the goal is to reach this part. Random actions are, I mean, just random moving, right? You can move to this goal place. You can also move to other places. Yeah, it keeps running. Since we are using this online platform, is a little bit slow. Actually, when I tested in my local computer, it's actually very fast. You can see continuously the animation, how it works. Okay, so so I can stop it. So also I may show you some actual information because okay, it is too small. So you see this env dot period step with action, then it returns some information for this environment. We have this observation and the reward. Actually, we can print out this observation and reward information to see how they define their environment. Okay. Actually, I'm not sure if we can just print observation and reward. If you run this way, those data will keep printing here. So let's see if we can see clearly. Yeah, here. So you will see the first part, this array is the environment. This part is the reward. Okay. So the environment includes multiple data information. And while it make action, and some action generate a good reward, some action generate better reward. And this environment, I didn't check the detail about this environment. They may related to some the position information, like whether it's in close to this position or somewhere else. Oops. Yeah. Okay, so that was previous iterate round, first round is the later round. So yeah, this is kind of a simple example for the state space or observation state. And this is the reward. Okay. You can also check, okay, let me stop. We can also check the action space, right? What is the action space here? Print env. action space. Let's see. Okay, so this action space is just discrete 4. It has 4 actions, and it follows the discrete the what is that, the method or approach inside of this platform, inside of this library. Okay, we cannot see the detail. Okay, anyway, so yeah, this is one example. For example, here there's a lunar lander. There are also other environments you can try. Let's go back to our slides. Okay. So as I mentioned, so just in case you want to run it fast, so you can also run this environment in your local computer. In my case, because I installed the WSL. Okay, so later in the slides I use Ubuntu in Windows. You can install WSL in Windows OS and set up Ubuntu terminal and the environment. You can run similarly. So in my case, I just open this terminal. Then I already installed the Ubuntu. What is this? Okay. So if I just open it, then it will run the Ubuntu system for me. And now in that case, actually, I also use VS Code. If I open VS Code, so okay. Okay. Okay, okay, I made the example here. So you can also write the code here, and I also, inside of this VS Code, there's a way to connect to the WSL. So this, if I select here, you see there's a way connect to the WSL, which is the Ubuntu. So the reason we are using Linux, not the Windows, is that there's some package that is not very convenient in Windows. Okay, for example, this Swig, actually Swig. So it's in Linux. In terminal, you can easily just install. In Ubuntu, you can just easily install Swig. But in Windows, you need to download the file. Actually, there's no installation file for you. Then you need to move this Swig library to some location and add the path to the Windows system. Let the program automatically search this Swig program. So it's a little bit complicated. Yeah. So then if you want, you can run here. Inside of this VS Code, you can also run Jupyter Notebook. It's or IPy Notebook. Okay, you don't. It's just another, just similar to this Google Colab environment. So IPy Notebook, you can just download it and run it in your the WSL system, the Ubuntu. Okay. So as I mentioned, so let's look at this environment. The fundamental building block of Gym is a env class. So it's a class. Then it implements the simulator that runs the environment you want to train your agent. So inside of this environment, that encapsulate some internal process by step and reset. So mostly when we run this IR process, we just run the we make an iteration and run the step. Each time we run one step and we generate some reward information, and eventually we can reset all the data. So if you click, yeah, there are okay. There are several methods in this environment class: step, reset, render, and close. The most important method is the step. It updates the environment with actions, returning to the next agent observation. So the reward for taking the action, so it actually just returns a lot of information. Observation, reward, whether the environment is terminated or truncated, and some extra information for the environment, some matrix or debug information. And after finishing this, all the process, the running process, you can reset your environment, like return to the original state, like try to not to save the run the data you already got, right? And render is to actually we use the render in this code, right? Yeah, we use the render here actually. Render is for visualization. When we design the render mode, which is RGB array, it will return every step. It will return one RGB image for you. So it's like a matrix. Yeah, three-dimensional matrix. It's like RGB. So each so it's give you a image. So that's why we can see the image below when you run it. And but we use a little bit. We use a matplot to show this image, show this RGB image, and to show here. And every time we clear output, then we show again. Clear output, show again. Clear output, show again. So it's memory efficient, but it's a little bit slow in this online platform. Okay, because they have need to transmit the data. And the close at the end of this simulation or process, we need to close the environment. And because the reason sometimes when there's some data, right, or this model may connect to some database, some other information. So if you don't close it, those data may not be correctly saved. That's why at the end of the simulation, you need to close the environment. Then in that case, the data may be correctly saved. Main attributes. So as I mentioned, it's just like the actual implementation of IR in this environment. Action space, observation space. They use observation space instead of state space. I guess state is too general. Observation space is more proper to describe because most of the time we cannot fully observe the environment. Then reward range. So the reward range is a tuple corresponding to the minimum and the maximum possible reward for an agent of an episode. The default reward range is set to infinite. Okay. So I guess so this reward range we also need to define. No, observation space. Observation space, as we showed you, it just shows you some the environment is already gone. Okay. Just shows when you print out, just show you a matrix or array, or if it become a complicated, it become a matrix, and they show you those environment information. And action space, yeah, the action you can do, whether it's a discrete or continuous. Continuous may be a little bit difficult to show, but yeah. And some of you may not be familiar with Python. I don't know. I guess most of you are familiar with Python, right? So but just in case you are not familiar with the Python, you need to check some tutorial for the Python. Python is not that difficult, but for some advanced topics, a little bit tricky, but you can check those tutorial to see those, yeah. And how you can install the WSCR in Windows OS. So there's a link. You can follow this instruction, how you can install a Linux on Windows. That's what, then in this case, you don't need to install the virtual machine or any other platform. It will be easier. Just simple, open the PowerShell, type this command, install. So open the PowerShell with the administrator mode, okay? Then install, it takes some time. By default, it will install Ubuntu for you. And after that, you can just open the terminal, then it will show you the Ubuntu terminal, then you can run it. So before, let's take a look at this, the gym environment. So at the same time, you can explore this gym environment. There's a basic usage, and there's an environment and a space, register and make. You can you can define the spaces. There's the fundamental spaces, composite spaces, and spaces utilization. There's a lot of methods you can use, you can manipulate to build some like environment or some environment you want to try. So wait, let me show you the right hand side. So basically in the environment, in this gym library environment, they already divided, kind of give you some predefined pattern: white box, discrete, multi-binary, multi-discrete text. Yeah. So for these spaces, you can, the box is simple, right? It's just like a 2D map give you. Like a box represents the Cartesian product of the unclosed intervals. And this is discrete. So previously, when we look at this code, the action space actually is discrete, with four elements in this discrete space, right? Then the finite subset of integer, it can, so it's, you see this integer. So it means that it has, if you build this discrete 2 or 3, it will just generate. So each generate multiple number, and each number represent one action, okay? Then when you sample this, when you select the action, but here this is observation space, so it's a little bit different. So if it's action space, then it's multiple action. If it's observation space, it means that we are kind of use a discrete environment. And other you can explore the binary, the 0, 1, right? Multi-binary, N-shaped binary space, multi-discrete, a lot of predefined spaces you can explore. And from here, so the composite space, it can based on dictionary, tuple, sequence, and graph. So I guess most useful is a graph, right? You can build the complicated environment based on the graph. Wrappers, so I will not. So now we come to this environment. So you will see there's all kinds of different environment. Classical control, box 2D, Toei, Mujoko, Atari, and third-party environment. So if you look at you see this kind of classical control, then every one of them has an environment. So they already predefined the environment. For example, this cut pole, the purpose is to maintain it straight, right? Just to be standing there. You move left or right to make it stand. And then you can train this agent to make the good decision, to keep running it. Yeah. And the mountain car, pendulum, yeah. And so this is for the classical control. The next one is box 2D, right? Okay, it's a little bit. Box 2D, there is a biped walker car racing lunar lander. The lunar lander we were just seeing, right? And car racing is here, this one. So you can okay, for each this environment, you will see how they define this action space and the observation space and how you can use it in your environment. So for example, this action space, it has this I don't know, this is the X, Y, Z or the angle information, or this is acceleration or deceleration. Yeah, there's some information. It's the action space. The observation space is we may need to check. Maybe this is RGB, the color of this image, and yeah. Then this is the size, or the intensity of each pixel, and how you can use it. So okay, yeah, there's a actual detailed description. For example, here the action space, if continuous, there are 3 actions: steering, minus. Okay, yeah, the first one is a steering, a -1 to +1, 4 left, 4 right. The gas, acceleration, braking. If it's discrete, there are 5 actions. Yeah, so it's these 5 actions. It's already kind of predefined discrete actions. Do nothing, steer left to right, gas, and brake. Yeah, a little bit different from the observation space. Yeah, it's like top down, this RGB image for the car. It's like they detect the racetrack based on the RGB, the image. Then if the racing car move out of it's a race track, it get penalty. If it's keep moving in the track, then it has a positive reward. Then reward, the reward is the minus 0.1 every frame, and with plus 1000 divided by n for every track type visited, where n is the total number of types visited. Now it's become complicated, right? It's very detailed definition of the reward. If you finish the 732 frame, your reward will be 1000 minus 0.1 times that reward. Okay. It will be this point. So okay, so because the reward, they consider the track, only consider the track type, right? Okay. So this is how you can like explore this different kind of environment. Let's take a look at other environment. For example, this Mujoko. This is very general, like robotics environment. It can be ant, cheetah, hopper, humanoid. This pusher, reacher, different kind of a mechanical environment. Actually, they have a lot. Then Antaria is a set of games. It has 2,600 environments simulated through the Stella and other environment. So for this gaming environment, you can train the agent to play the better games, like to be surviving for a longer time. Okay, there's a lot of more those environments. But I guess when you install it, it will become very big. Okay, action space. Yeah. So they also define this kind of action space. They become very complicated, right? So there's a up fire, down fire, right fire. Then observation space is also based on RGB. It can also be the gray version. RAM state. So the rewards, the exact reward I mean depends on the environment and are usually documented in the. So it depends on different games. You can define different kind of rewards. The mechanism, okay, stochasticity. Oh, okay. So this is for the they are built-in. They also have so many. Third-party environment. So in this third-party environment, you will see a lot of state-of-the-art research. For example, at the beginning, when I introduced this environment, when we talk this gym is a single agent RL environment. If you want to run multi-agent environment, well, we can use this petty zone. So this environment build this multi-agent. You can train multi-agent to run the simulation. There's also offline, grid world, robotics, and multi-objective IR, many agent IR. So actually 3D navigation. 3D navigation is like the 3D game, okay? Or you can do some like flying navigation, yeah. So if you scroll down, many of them have the SOTA, the state-of-the-art implementation and their algorithms, how they achieve the best performance. Yeah. For example, this robotics environment using pi-bullet physics engine. This is for the video game, and they can link to the utility. Unity machine learning agents. Okay, environment for Unity game engine. This is for robotics environment. Then you can simulate UAV flight simulator, real world simulation. Yeah, all kinds of the environment. You can autonomous driving environment and other environments. Okay, so since we are choosing the finer as a term project, so you need to decide. I may also consider some topic for you, and also you can consider by yourself what kind of interest topic you want to work on it based on this different kind of environment, or you can explore. Yeah, there's many topics here, and explore some interesting topic and try to work on that topic, try to implement some algorithms and run the algorithm, get the, if you can, improve, find some performance issue, then you can improve, then that will be better. Okay. So let's go back to. So far, any questions? Okay. So then, I will find really related chapter for this today's content, and for those contents, then you need to write some summary for your reading. What you got? Any thinking, any thought you got from your reading. Okay. And what else? So also, I received the email from the university saying that next week, soon the campus will have the
the festival. So then the Friday lecture, I don't know how many of you will go to the student campus to join the festival. So, and depends on the schedule. So the university sent an email saying that the professors can kindly consider to have online class for students to join the festival in the campus. So I don't know your schedule. And we will have an offline class here, or you want to have online class? Online class, raise your hand. 1, 2, 3, 4, 5, 6, 7. Okay, half, 50%, 50%. Hard decision. Okay, so let's see. So yeah, let's see if before the next lecture that I will in the next time I will announce in the iCampus to decide whether we have a online lecture, pre-recorded lecture. Yeah. Okay. Yeah. Thank you for your attention. And we finish today. Yeah.